And we are now recording. Let's get the current slide up. But I wanted to mention this. I think I announced it before, but just in case you weren't here or I didn't get it announced, because it's been so long since we met. This is a private company as far as I can tell, and I don't know why we're advertising for them, but they sent it around for us to make the announcement. It's concerning, the name of the company is STEM Jobs, STEM of course standing for Science, Technology, Engineering, and Math. And this is a new tool to connect classrooms to careers, is what they say, and to connect students to opportunities from post-secondary institutions, employers, military, and stuff like this. So here's this STEM-type navigator. If you're interested, you can certainly grab this piece of paper. You can even have this piece of paper. I've announced it several times now, so I'm quite willing to give it up. If you want to check it out, you certainly can. Sounds like it's a good deal. I just don't know why we're advertising for them, but sounds like it's a good deal. All right, any questions on anything we've done so far? Okay. And the others were looking at the first test. If you want to see yours right after class or something, you can. I just can't return them yet because I don't have them all in yet. So, and the second test, 4 of you have turned those in, so please continue working on those because we're moving along in chapter 3. Okay. No questions? Anything we've done so far? Okay. Now, sorry, I had a treatment on Friday, and before the treatment, my neutrophils were very low, platelets low, red blood cells low, everything low, including the white cells, which are what we wanted to be low. And now I've got conjunctivitis. It happens almost every time. Once it knocks down my immune system, that seems to be what pops up first. So if my eyes start watering and that kind of stuff, I'm trying not to rub it, but it's just sort of a pain. But also, if I get extremely exhausted, say, let's just take a break, we'll do that too, because the fatigue, because of the low blood cells, low red cells, and hemoglobin and hematocrits. Sometimes we get to me. This weekend, Friday, I slept most of the day after the treatment. So, but I had a decent weekend after that. Still just get really tired. All right, if there's no questions, we mentioned this before. I think we talked about it. I don't know if we actually went over the slide. Do you recall? It's been a week now. Here is the definition of a point of inflection. If f is a function that is continuous, hey, number one, got to be continuous, okay, on some open interval, and let C be a point in that interval, okay? If the graph of f has a tangent line at the point C, f of C, okay, if it has a tangent line at that point, then that point is a point of inflection of the graph of f when the concavity of f changes from upward to downward or downward to upward at that point, okay? So, just to get a parallel, you might say here, when we were dealing with, all right. When we were dealing with first derivatives, what we were interested in was extreme values, okay? Whether it's a max or a min, okay? And if, in that case, what we were looking at, if the slope of the tangent line changed at a point, then it had to be an extreme value, a maximum or a minimum. Now we're looking at, it rains, it pours, good, here they come. All right. Taylor, is that right? Taylor? Is it Taylor? Is it Taylor?
Katie.
Huh?
Katie. Yeah.
Okay, got it. Sorry. There you go. Okay. And All right, I think I got everybody. All right, we were just talking about points of inflection, and I was sort of making the parallel when you're dealing with a first derivative. What you're looking at is a change of slope. Anytime you have a change of slope, I mean, you could almost take the same sentence here and say if alpha is a function continuous on open interval, C is a point on that interval. If the graph of alpha has a tangent line at the point C, alpha C, then this point is a extreme value, a critical point of the graph when the slope of f changes from positive to negative or negative to positive. That's an extreme value. That was your first derivative test. Now we're doing second derivative, and a point of inflection is very similar, except now we have f has a tangent line at the point C, f of C, and that point is a point of inflection, not a critical point, a point of inflection of the graph of f when the concavity changes from upward to downward. That's a point of inflection, or downward to upward. That's a point of inflection if that happens at that point. Okay? To locate possible points of inflection, how do we locate our extrema? Set the first derivative. What were the two conditions on the first derivative that could lead to an extrema? Okay, either undefined or equal to 0. Guess what? Same thing here. Only now is second derivative, for which the second derivative is 0, or the second derivative does not exist. This is similar procedure for locating relative extrema. That's what I was saying. And here's the theorem that backs it up, the points of inflection. If C, f of C is a point of inflection on the graph of f, then either f double prime of C is 0, or f double prime at C does not exist. That is your point of inflection. Okay. Now, okay. Ready for example 3. Okay. This is on sort of the top of page 194. And for those who just came in, I'll apologize ahead of time if I start squinting and blinking too much. I had a treatment on Friday, and going into the treatment, my everything was low, and I'm sure it's even lower now. And what happens after a lot of the treatments, I'll get conjunctivitis the very next week, and it seems like that's happened. So this eye is just driving me nuts, but we'll try to go from here. Okay, determine the points of inflection and discuss the concavity of the graph of this function. F of x is equal to x to the fourth minus 4x cubed. What would be the first thing you would do? Take a derivative. Good choice, okay? Let me get my pen set up. Okay, so f prime of x is equal to, help me, 4x cubed minus 12x squared. Okay? Does that tell us anything about a point of inflection? No. That could tell us about extreme values, and we may be interested in those. Most of the time we are. But in this problem, it's just asking about points of inflection. So what's the next thing we've got to do? Take the derivative again. Take the second derivative. Okay, f double prime of x is then going to be what? 12x squared minus 24x. And what do we do with it?
See where it's negative and positive.
Okay, in just a minute we'll do that. First we set it equal to 0. Or, what's the other thing we do? Investigate where it doesn't exist. Okay? But this is a polynomial function, right? its first derivative, its second derivative. All its derivatives are going to exist everywhere, okay, because it's polynomial. So we don't have to worry about the places where it doesn't exist, only where it's equal to 0. And what do we go from there? Say again? Okay, not yet. When you got especially a higher order equal to 0, what you want to do is, what's the F word? Factor. We want to factor and see if we can split off values. So let's factor that. And what do you get?
12.
Say again? 12. Not quite. Factor it completely.
Can you not pull out a 12?
Yes, you can. Okay, we'll do it. Okay. 12 times, and what do you have left? X squared. Minus 2x. Okay, that's equal to 0. And I'll tell you what I'm going to do right now. I'll divide out the 12, because 12 can't be equal to 0, right? So it's gone. So we don't have to worry about that anymore. Can you factor any further? Anybody? Factor out an x. And what does that leave you with? X minus 2. And that's equal to 0. What does that tell you? Either x equals 0 or x equal 2. Okay? Now your earlier idea is a great one. Okay? We want to see what's happening to that second derivative at these 2 points. Okay? At x equals 0. Okay? So let's get something a little to the left of 0. What would that be? -1. Okay? At x equals -1, see what would be the easiest one to plug into. Probably, why not this one? Okay, at x equals -1, that of course is x is -1, and x minus 2 would be -3, and -1 times -3 is positive. Who cares what the value is? It's positive. Okay, let's do something in between these two. What would that be? 1. X equals 1, what do you have? 1 times -1, right? 1 times -1 is negative. So here, indeed, at x equals 0, your positive concavity, meaning concave up, coming into 0, but concave down after 0. Definitely a point of inflection, right? Okay, how about x equals 2? We've already determined what the concavity is at x equals 1. What was that? -1. Okay, so that's negative. How about something to the right of 2? 3. Okay, what would you have here? Times is the main thing is positive. So you went from negative to positive, so sure enough, you do have a point of inflection at x equals 2 as well. Okay? So 2 points of inflection, one at x equals 0 and one at x equals 2. Now, the only little deal here is that it's asking for the points of inflection. A point is an ordered pair. If you're in 3-space, an ordered triplet, or whatever. But all we have are x values. So what we need to do is find out the y value as well. How do we do that? Really easy question. Plug it into the original thing, and what is your, when x equals 0, what's your y? 0. Okay. And when x is equal to 2, what's your y? Whoa. 2 to the 4th is? Anybody? 16 minus
negative 16.
-16. Okay. Sounds right, because negative 4 times 8 is negative 32. 16 minus 32 is negative 16. So there are your 2 points of inflection. Let's see if I remember right. At 0, 0, it's going like this, and at 2, negative 16, it changes from negative to positive. Okay, so 2 points of inflection. Okay, now I didn't draw the graph, and I would just as soon not draw the graph. Let's take a look and, well, let's see how they did it. Okay, determine the points of inflection and discuss the concavity of the graph. Okay, we didn't do that. What's the concavity of the graph everywhere to the left of this? We already basically did it. It was negative, right? No, it was positive. It was positive to the left, negative in between, and positive to the right. Okay? So yeah, we did discuss the concavity everywhere. Because guess what? It can't change again. The only way it could change again over here is either have a point where that concavity didn't exist or whether it hit 0 again. And since it didn't, we know what the concavity is. So let me erase this if y'all are okay with it. And let's see how they did it. Differentiating twice produces the following. F of x is x squared minus 4x cubed. That was exactly what they gave us. F prime is 4x cubed minus 12x squared, exactly like y'all did. And F double prime is 12x squared minus 24x, which they went on and factored. We did too, but we took it one extra step. 12x times x minus 2. Okay. Now, that second derivative, to determine points of inflection, you either set it equal to 0 or see places where it doesn't exist. It exists everywhere. So we're only interested where it's equal to 0, and that's x equals 0, x equals 2, just like we did. Okay? By testing the intervals determined by those x values, you can conclude they both yield points of inflection because the concavity to the left was up because the second derivative was positive, in between was down, second derivative was negative, and to the right was up again, so you had a change of concavity here, change of concavity there. Change of concavity is a point of inflection. And here's how the graph looks. This one coming down here, concave up, everywhere to the left of 0. And not only is the concavity equal to 0 here, the first derivative is equal to 0 here. Now, just because the first derivative is equal to 0 doesn't guarantee you have an extreme value. In fact, here you don't. It looks like it's going to be a relative minimum coming in. It looks like a relative maximum coming out. That's a point of inflection. It's not an extreme value. Okay? This one, however, we are concave down here and concave up here. This is not a first derivative equals 0. This is strictly a point of inflection. Okay? This is a critical value as well, but it's a critical value that does not produce an extreme value. This is not a critical value, but it is a point of inflection. Does that make sense? Points of inflection can occur either where the second derivative is 0 or where it does not exist. This exists everywhere. And it's concave up from there on. Never changes again. Any questions? Okay? That's what points of inflection look like. Concave up, concave down, concave down, concave up. Now looking at them, it's real hard to pick them out, okay? Because it looks like anywhere along this stretch here, it's almost a straight line, and it's hard to tell the concavity, okay? But, you know, using the numbers, you know exactly where it is. All right, any questions? All right, now, remember 3.8? That, let's go back and just hit it real quickly. 3.8. If C, f of C is a point of inflection of the graph of f, then either f double prime at C is equal to 0 or f double prime at C does not exist. Okay? Does that mean it goes the other way? That if you find a place where the second derivative is 0 or doesn't exist, does that guarantee a point of inflection? No. Remember, the same thing went for first derivatives. In fact, we just saw an example of it. The first derivative was 0 at 0, 0, but that did not conclude that you're going to have an extreme value there. You did not. So the same thing is true here. Just because you have second derivative equals 0 or doesn't exist, doesn't guarantee you've got a point of inflection. That it is possible for a second derivative to be 0 at a point that is not a point of inflection. Okay? Here's an example of that. Okay? F of x equals x to the fourth. What would be the first thing you would do? Take a derivative. That would give you what? Say again? F prime of x would equal 4. More than that. X to the third. Does that tell you anything about points of inflection? No, that tell you possibly something about max or min, but not point of inflection. What would you have to do next? Take the second derivative. And what's your second derivative? 12x squared. Okay? And what do we do with that? Set it equal to 0. Or find out where it doesn't exist. Well, that's again a polynomial function. It exists everywhere, so there's no place where it doesn't exist. So, at what value of x would that be 0? X equals 0. Okay? Does that guarantee you have a point of inflection? No, it guarantees you investigate that point. So let's take to the left of 0. Right? Negative 1. And when you plug that in, what do you get? Positive 12, so it's concave up there. And then take something to the right of 0. Say 1 again. That's 12 again. Again positive. So you do not have a point of inflection because you did not have a change of concavity. Even though the second derivative was equal to 0, it didn't change signs. Yes?
Take the second derivative.
What's that?
What's the purpose of the second derivative?
What is the second derivative? Or what
Why are we taking the second derivative?
Why am I taking the second derivative? That indicates where you might have a point of concavity. It gives you concavity. Yeah.
Why you didn't use the first?
The first derivative only tells you whether you have an extreme value or not. Relative minimum, relative maximum. You do here a relative minimum. Okay? Set that equal to 0, that tells you that. It doesn't tell you anything about concavity, though. You have to take the second derivative there. That will tell you about points of inflection. If you have a change of concavity, you have a point of inflection. If you do not, you don't have one. Even though it's 0 there, the second derivative is 0, it's positive on both sides of that, so it's not a point of inflection. Okay? So the second derivative is 0 when x equals 0, but the point 0, 0 is not a point of inflection because the graph of alpha is concave up on the left and concave up on the right. Second derivative is positive on both sides. So not a point of inflection. But that's where you test it to see. Okay, does that make sense? Same thing we did with maximum and minimum. The first derivative lets you know where it might be. It doesn't guarantee you there's one there. Okay. Now, that leads us to the second derivative test. Okay? I was just looking. There's this little exploration on the side here. And it's worth a read, but I don't think it's worth going over in class. Okay, second derivative test. Okay, in addition to testing for concavity, the second derivative can be used to perform a simple test for relative maximum or minimum. Remember, before we had to look at both sides of your critical points to see if it's changing slope. Now that we know what the second derivative does, we don't need to do that test anymore. All we do is take the second derivative, and if that second derivative is positive at the point of the maximum or minimum at our critical points, if it's positive, guess what? Got to be a relative minimum. If it's negative, got to be a relative maximum. Every time. So there's no reason to go back and do all the little tests that we did before. We can just use our second derivative. Since we're going to use it for concavity anyway, let it do. So this is actually easier than what we were doing with the first derivative test. The test is based on the fact that the graph of a function is concave up on an open interval containing c, then f prime of c is 0, okay, and f prime of c is equal to 0, then f of c must be a relative minimum. If it's concave up at that possible maximum or minimum, it's got to be a minimum. If it's concave down at that possible, at that critical value, it's got to be a maximum. If, however, the second derivative was 0 there, you don't have a conclusive test. So similarly, if the graph of a function is concave downward on an open interval containing c, and f prime of c is equal to 0, making it a critical value, then f of c must be a relative maximum. If it's down at c, concavity is down, it's got to be a relative maximum. Concave up, concave down. Okay, now notice what has to be true. First derivative equal to 0 there, and second derivative positive, concave up. First derivative equal to 0 there, second derivative negative, concave down, relative max, min, relative max. Okay. Make sense? Okay. To me, much easier than testing on either side. Okay. So here's the second derivative test. Let f be a function such that f prime of c is equal to 0. Not the higher. And the second derivative of f exists on an open interval containing that value c. Okay? If f double prime is greater than 0 at that point, that means it's concave up, that's got to be a relative minimum. Got to be. If f, the second derivative is less than 0, not 0, but less than 0, then it has to be a relative maximum at that point. Okay? And you guarantee it's an extreme. You don't have to test to see if it is an extreme. That guarantees it. And it tells you which way it's going. If f double prime at c is 0 and f prime at c is both 0, the test fails. You just don't know. F may have either relative maximum, relative minimum, or neither. It may be, if f double prime is 0, it could easily be a point of inflection. Or not. It doesn't have to be a point of inflection. In such cases, you then go back and use first derivative test to tell which you have. So you don't get out of the first derivative test always. If that second derivative is 0, no guarantees. Okay. So let's do example 4. And by the way, example 4 is one of these that at larsoncalculus.com you can find the interactive version for this type of an example. So here's what we have. Find the relative extrema. We're going back to doing relative extrema for f of x equal negative 3x to the 5th plus 5x cubed. How do we find relative extrema? Take a derivative, okay? Always a good answer, most of the time anyway. F prime of x, what would that be? Second? Negative 15 x to the 4th plus 15 x squared, okay? And if you're looking for extrema, what do we do with that first derivative? One of two situations. How many times have we said it today? and last time, and several times. Set it equal to 0, exactly, okay? Or investigate where it doesn't exist. Is there anywhere that doesn't exist?
No.
No, it exists everywhere. It's a polynomial. It exists everywhere. So we set it equal to 0. What are our critical values then? The places where that's equal to 0. What's the next thing we do?
Take it a second.
Second?
Take out 15x squared.
Okay. Factor out, I would take out the minus 2. You like your minus signs, but I don't really care for it. 15x squared. And what do you have left?
X squared.
X squared.
Minus 1.
You took out the minus, that left that being a minus 1.
I said minus.
Yeah, okay, sorry. Huh?
I said minus.
Oh, okay, I couldn't hear. I heard someone say plus, but okay. Set that equals 0. Okay? What does that tell you?
X plus 1, x minus 1.
Okay. All right. Those are two critical values. X equal 1 or x equal negative 1. Any others?
X equals 0.
X equals 0. We have three critical values. Okay? Now, how do we determine whether these are max or min?
Plug them in.
Okay, if you plug them in, you're going to plug them in where? For f of x or f prime of x?
X.
Second,
F of x.
f of x will just give you the values for them, which you will need to know, but that doesn't tell you whether they're max or min. How do you, second? Take a second derivative, exactly. So let's do f double prime of x. And what does that tell you? Go back to this form, okay? What will that tell you? Help me, help me.
It's CC.
Negative 60, is that what I heard?
Yeah.
What else?
X cubed.
Cubed
Plus 30.
plus 30,
X.
x. And what do we do with that second derivative? You really don't have to do anything with it now. If you're looking for points of inflection, then you do something with it. All we're going to do with it now is evaluate the second derivative at those 3 points. Okay? So let's do f double prime at 0. And what does that give you? It gives you 0. What does that tell you? Nothing. Okay? It tells you we can't tell. It may be a max, it may be a min, it may not be either one. Okay? So we're going to have to do the first derivative test on that. Okay? Let's do the other two. F double prime at 1. What will that be? F double. Second?
X squared. I said negative, no. Negative 30x squared, not cube, like you saying something.
Okay. We're putting x equal 1. So when you cube 1, you get 1. Right? You get negative 60 plus 30 is negative 30. Okay. What does that tell you about the critical value x equal 1?
Concave downward.
Yes, definitely concave downward, way downward, right? Negative second derivative. And what does that tell you about its extreme value? If it's concave down at that point,
It's a flesh.
it's got to be a max, right? If it's concave down, that's why I can hold my hand like this. That's got to be a max. Got to be, absolutely. Okay? Let's do f double prime at negative 1. Our other potential, our other critical value. And what would that be?
30.
30, which tells you what? Okay, that's a positive value, right? A very positive value. Meaning, what does the second derivative tell you? It's a minimum, concave up, really concave up, so this has to be a minimum, right? Because that's a positive value. This negative value, concave down. Positive value, concave up. That means that one has to be a minimum. Yeah, okay. Concave up, and that has to be a maximum. Okay? Now, since we know these two values, okay, something to the left of 0, something to the right of 0, to the left of 0, this is concave up, and to the right of 0, it's concave down. What does that tell you about f at 0? What do you call a point where the concavity changes? A long time ago, at least 30 minutes. Huh? Point of inflection. That means that's the point of inflection, meaning neither concave up nor concave down, because it's let's see, get it right. It's concave up coming into it, 0 at it, and concave down past it. That's got to be a point of inflection, neither a max or a min. So you didn't have to go back and do the first derivative test, because your second derivative test lets you know that. Okay? You don't always get that benefit, but this time you did. All right? Let's see how they did it. In fact, hopefully they will draw a picture too. Okay? First thing they did is begin by finding the first derivative, and you get that to be 15x squared times 1 minus x squared. Okay? Now, they did it that way. We factored out the minus 15x squared and gave you x squared minus 1. It really doesn't matter because you get the same values. From that derivative, you see that either x equals -1, 0, or 1. 3 critical numbers for f, and only 3. Okay? That means these are the 3 places where you could have a max or a min. And that's what we're looking for at relative extrema. So, by finding the second derivative, which is, and again, they pick a weird way to do it, 30x minus times 1 minus 2x squared. I would have factored out a minus 30x and left it 2x squared minus 1, but it doesn't really matter. You can apply the second derivative test. So we did that, we did it, and we found the second derivative was positive at -1, okay? Now we did go back and evaluate the point. That's one thing we didn't do. Sorry about that. I forgot to do that, but you would have to anyway, okay? And that's a relative minimum there, okay? It's 0 there, the test fails, but over here you got a relative maximum because that second derivative is negative there, okay? So we have a relative maximum. Now, without doing anything else, you can now see, well, the second derivative is positive to the right of 0, negative to the left of 0. That means it must have a change of sign at 0 because it's 0 at 0. So therefore it's concave up to the left, down to the right. That must be a point of inflection. Neither a max nor a min. Okay? But they say because the second derivative test fails at 0, 0, you can use the first derivative test. Not necessary. Okay? You can do it for sure, absolutely. Observe that f increases to the left and right of 0. Okay? So the first derivative is increasing to the left and increasing to the right. Now what we didn't do was find the points, and I should have done that, because if you go back to the original problem, find the relative extrema, those are points, not just x equal, the points. So when you found x equal -1, you could plug that in here and say f of -1 is equal to what? A little louder?
I'm going over it in my head.
Oh, okay. It'd be a minus 3 times negative 1 to the 5th plus 5 times negative 1 cubed. And what's negative 1 to the 5th?
8.
Huh?
8.
Negative 1 to the 5th is?
Oh, it's going to be what? Negative 2.
Okay, negative 1 to the 5th is?
Negative 1 to the 5th is positive 3.
No. Okay. Oh, okay. Yeah, okay. You're doing the whole thing. That does come out being positive 3, and this comes out being? Negative 5, so this is negative 2. So there's your first point, negative 1, negative 2. Okay? Then you do f of 0. That's your second critical value. And what's that? 0. Okay, so your second point of interest is 0, 0. That's your critical point. Okay? And your third one is f of 1. And what is that?
2.
Positive 2. Okay? So your third point is 1, 2. Okay? Now, this is not quite fair to do, but it is doing it. If you picture this, negative 1, negative 2, it's down here. 0, 0 is here. And 1, 2 is there. This had better be a minimum, okay? You would think it would almost have to be. But you do your test to make sure. Second derivative shows it is a minimum. This one, well, it's in between these two, so it's sort of hard to see how it could be either a maximum or a minimum. And sure enough, it's not. It's a point of inflection. This one, you would guess, would have to be a max. And sure enough, when you look at it, yep, minimum here, neither here, maximum. Okay. Now, that's not a guarantee. You need to do all your steps, but at least that makes you feel fairly warm and fuzzy that you got the right answer, right? Okay. Whoa. Is that it? Yes, it is. You're absolutely right. So homework exercises for 3.4 are do number 3. We've already talked about that before. And that's at calcchat.com as well. Then answer in the back of the book and worked out solution at calcchat.com. Then do any of the odds 5 through 15. They're all at CalcChat. 13's at CalcView. Do any of the odds 17 through 31. They're all at CalcChat. 17's at CalcView. Do any of the odds 33 to 43. They're all at CalcChat. 37's at CalcView. Do either 45 or 47 or both. They're both at CalcChat, but neither one of those are at CalcView. Exploring the concepts. I don't know if there's even an answer in the back of the book or anything at CalcChat. I'm assuming there is because they said that it would be. But you can do that, decide whether you're going to do that. But number 51, definitely do sketch that graph. That's at CalcChat, not at CalcView. Then either 53 or 55, they're both at CalcChat. 53's at CalcView. And there's a think about it at 57. I don't know if there's an answer at CalcChat or not, or in the back of the book or not, but you can take a look at those. There's a conjecture at 59, and again, you can look at those if you like. You should be able to do 61. It's at CalcChat, not at CalcView. And I would say you choose any of the odds 65 through either 65 or 67. Do one or both of those. They're both at CalcChat. Then do either 69 or 71. They're both at CalcChat. And then do 73. It's the only one like that. And there's a 75 and 77 are true false, so you can take a look at those. and then there's a proof 79. You can do that if you choose. I'm not going to assign that. All right. Now, there's this section on limits at infinity. You know, just that statement doesn't make any sense. If you're at infinity, where would be a limit there? There can't be. You're at infinity. It's just increasing or decreasing without bound. So basically, you're just saying it's going to infinity. Well, then why talk about a limit there? Okay. There is some value. Say when x is going to infinity, you could have a horizontal asymptote, so you may have a limit there. But when y is going to infinity, you don't have a limit. You may have a limit on x while x is approaching. So this section, and because we're running out of term and we really have a lot of pretty important stuff to do, I would say review this on your own. I'm not going to test you on 3.5. Okay? However, in paging through this, you'll find Maria Gattina Agnesi. Haven't seen many women, have you, in math books? She was one of a handful of women to receive credit for significant contributions to mathematics before the 20th century. And you can read about this. Pretty fascinating character, sort of a sad and twist on it. She came up with actually a function that was very intriguing and interesting and had some application, I'm sure. And they named this function in Italy, in Italian, I can't pronounce, I don't know Italian, but veterare or something like that. A curve that came up because of the mistranslation of the Italian word veterare. They translated that to be a witch. Now that's really bizarre that they would take something found by a woman and name it a witch. Okay, that's almost too coincidental. And that's to this day it's called the Witch of Agnesi, which has nothing to do with witches. It's just the shape of the curve. But anyway, there's a potential paper topic or two or three that you might find there. Okay? And again, reading through this, going through it, you may find some things of interest, maybe even stuff that is beneficial to your field of study. But I am suggesting that we go to section 3.6. So we're going to pause here. If I had time, I'd just do a slideshow of 3.5. I think we need to move on. So let's discard that and go on to 3.6. Now, we've just barely been going an hour. This isn't a bad break point. Does anyone need a pause, a break here, or do you want to keep trucking? Okay. I really do need to do something with my, rinse my eye out or something because it's itching like crazy. So if you don't mind, let me pause here and that's not what I wanted to do, is it? Okay. Hit the wrong thing. I hope I didn't spot something up here. Okay. Okay, how do I get back? Here we go. We're back. Good. I thought I hit the button, but I didn't. recording, but I don't have projector on yet. So I'm waiting just a minute for that to happen. So let's get the slideshow set up for current slide. And here we go. All right, we're still in chapter 3. I thought it was better and now it's worse again. Applications of differentiation. And now we're going to do a summary of curve sketching. Okay? Basically, we're going to review almost everything we just did. Okay? But trying to tie it together perhaps a little bit better. So our objective is to analyze and sketch the graph of a function. Okay? And the first and basically only topic here is analyzing the graph of a function. All right. Bless you. When you're sketching the graph of a function, either by hand or using a graphing utility, remember that you normally cannot show the entire graph. Okay? These could go on forever. Okay? The decision as to which part of the graph you choose to show is often pretty crucial. Okay? Now, for instance, if you're using a graphing utility and you have a viewing window pretty well set to this, from x going from -2 to 5 and y is going from -10 to 40, that looks like you have a parabola, right? However, if you know that's your function, you also know that doesn't result in a parabola. Why? How do you know this will not result in a parabola?
The cube.
Second?
The cube.
Is a cubic function. And cubic functions, by the way, when remember back in pre-calculus algebra, if you have an odd exponent here, that means the function's going to wind up doing this. This looks like it's doing that, okay? That looks like an even exponent, maximum exponent. This is an odd. So expand your viewing window, and my word, look how far you had to expand it. From -10 to -30 on x, that's not too bad. From -1200 to 200 on y, you could have got by with 100, but still, that's a major expanse. So now you see that is indeed your cubic function. Okay? How do you know that's as wide as you have to go?
You see both maximum and middle.
Okay? Here's a couple things to recall. Okay? When you have a cubic function, the maximum number of zeros you can have is 3. Maximum exponent there. This shows 2. That doesn't mean there's not another one, unless you really think about it, and then you know there has to be. But when you see this and you see 3 zeros there, say, okay, expanding my scale isn't going to get me any more. This is going to continue to go up. This is going to continue to go down. We cannot find another 0 anywhere because we found the max. Second feature that you could think of, the maximum number of turning points here is 1 less than that. 3 minus 1 is 2. And sure enough, this has 2 turning points. Now, it doesn't guarantee you have to have 2 turning points, but I wouldn't stop looking until I said, I'm convinced that it's not. But the other thing, the main thing is, this thing had to be going in opposite directions. And when you see that's going down, that's going up, and you got your 3 zeros, 2 turning points, you can't get any more than any of those. So stop right there. Anything else is expanding your thing, it's just going to make this smaller and smaller, and you're not going to get any more information. Does that make sense? Okay. That takes you back to pre-calculus. Okay. By seeing both views, it's clear that the second viewing gives you more complete representation of the graph, but would a third viewing reveal other interesting portions of the graph? To answer this, you need to use calculus to interpret the first and second derivatives, which I was doing without calculus, but you can use calculus to continue. To determine a good viewing window for a function, use these guidelines to analyze its graph. Okay? Now this is talking mostly about using a graphing device. Okay? Determine the domain and range of the function. Okay? Well, let's go back to the one we had. What's the domain and the range of that function? Domain first. Remember that from pre-calculus algebra? Domain is? It's a polynomial function. All real numbers. Now, the range of this, and again, this is going back to the fact that's an odd exponent there from negative infinity to positive infinity. All real numbers there too. If this had been maximum exponent even, then you're going to either have, it's going up and up or down and down, so it's not going to go infinitely in one direction, or it's going to go infinitely in one direction, but not necessarily both. This goes infinitely in both directions. Okay? So, again, you have to pull back all the data that you know from before. Okay? So, identify domain and range. That function we nailed it. Determine the intercepts. Okay? What two types of intercepts could you have? X and Y. What is another name for your X intercepts? It'll be your zeros of the function. Set the function equal to 0, because guess what? X-intercept are where y is equal to 0. Places it crosses the x-axis. It only crosses the x-axis where y is equal to 0. And f of x is equal to y. So set the function equal to 0, find your x-intercepts. How about y-intercepts? How many might you have of those? No, x-intercepts you could have more than one. I won't say infinite number, but you could. But more than one. You could have easily more than one. Y-intercepts? No more than one. Why? Because y-intercept, by the way, that's where it crosses the y-axis. The y-axis is a vertical line. And how many times can a function cross a vertical line? Once and only once. It may not cross at all. Okay? If that's a asymptote, it won't cross at all. So, you may have multiple x-intercepts. Set the function equal to 0, find the x-intercepts. Set x equal to 0, you find your one and only one, if you have it, y-intercept. Okay? Asymptotes. What's going to be true about an asymptote? How many types of asymptotes could you have? Two. Actually, there are three types that you could have, but usually we deal with two. Either horizontal asymptotes or vertical asymptotes. Okay? Second?
What would be a third one?
The third one is what they call a slant asymptote. Occasionally you have it. Is that what you said? Yeah. Yeah, slant or oblique asymptote. Most of the time we don't fiddle with those too much, but you can have them. It is true. Goodness, my eyes are itchy. Okay. So usually we stick with horizontal and vertical. Vertical asymptotes are where a number can't be. Generally, where you can't divide by 0, right? If you have a 0 in the denominator, you better have a vertical asymptote there. Okay? Not always, but most of the time. Okay? Horizontal asymptotes, that's what's happening in the long run. Okay? So do your ratio of your leading, if you have a rational function, a rational function, ratio of your leading terms, and see what that's doing. That will tell you whether you have a horizontal asymptote or not. Okay, symmetry of the graph, that's your exponents. You know, are they all even, are they all odd? That'll tell you something about symmetry. Okay, locate the x values for which that first derivative and second derivative are either 0 or do not exist. What does that tell you? First derivative equals 0 or does not exist. What does that identify for you? Oh, we haven't done these, have we? Not more than 2 weeks worth. Okay. Critical values, which could be maximum or minimum, or neither. Okay. And how about f double prime? Either 0 or does not exist. Yeah. Points of inflection. Points of inflection. Okay? So use those results to determine the relative extrema and the points of inflection. There it is. First derivative relative to extreme, the second derivative points of inflection. Okay. Or not. Okay. So, it says analyze and sketch the graph of this function. Okay. What would you do to analyze the graph of that function? You tell me. What kind of function is that? It's called a rational function because it's a ratio of two polynomials, right? Rational function. Now, what are some things you can pick out here? Remember, let's go back to what we were thinking. Remember, we looked at our intercepts, that's both horizontal and vertical. Asymptotes, both horizontal, intercepts, x-intercepts and y-intercepts. Asymptotes, horizontal and vertical. And then your last thing would be basically your points, your critical points, which could be max or min, points of inflection, those kind of things. So, what's anything you can pick out here? Where do you want to start? Intercepts, asymptotes, critical points or values. You tell me.
Intercepts.
Second?
Let's start with intercepts.
Intercepts? Okay. What two types of intercepts could you have?
Vertical and
Okay, those are asymptotes. I said it wrong before. X-intercepts or Y-intercepts. Okay? I think of those as horizontal and vertical. You actually name them X and Y. Okay? What's going to be true about an X-intercept?
you can cross the x-axis over time.
Where it crosses the X-axis. And what's going to be true every place, at every value on the X-axis. Every value on the X-axis. What's true about every one of those? One thing
Y is equal to 0.
Y is equal to 0. And what's your Y here? I tell my pre-calculus class, the main thing to remember in pre-calculus, Y is equal to f of x. If you remember that, you got most of pre-calculus not. Okay? So your f of x is equal to 0. Okay? So first thing, to get your x-intercepts, set this equal to 0. That's going to give you the y values equal to 0. Now, where can a rational expression equal 0? The only place where a rational expression could equal 0. If that numerator is 0. 0 over 17 is 0. 0 over minus 3,400,000 is 0, okay? The only way a rational expression can be 0 is if the numerator was 0. What would make that numerator 0? 3 or?
0, 3.
Yes, those are your two places. So first, your x-intercepts, okay, will be at x equal 3 and x equal negative 3. And we know what the y value is, don't we? That would be negative 3, 0, and 3, 0. There's your x-intercept. Done. Okay? Any other intercepts we may be interested in?
No, because we already know the y. So
Okay, the y-intercept. Okay, what's going to be true about a y-intercept? X is going to equal 0. And what happens if you put an x equals 0 in that? In other words, we're looking at f of 0. X equals 0. What would that give you?
0 is
At 2 times negative 9 over negative 4. That would be negative 18 over negative 4, which would be 9 over 2. Positive. So your y-intercept, one and only one y-intercept. You may not have any, but this one is at That's your y value. So your x was 0, the y is 9/2. Done. You got your 2 x-intercepts, 1 y-intercept. You'll never have more than 1 y-intercept if it's a function. Okay? Next. Second. Asymptotes. Which one you want to go for first? The which? Vertical? And what will make the vertical asymptote? You never can have a 0 in the denominator, right? Any place that would give you that? Vertical asymptote, guaranteed. So how I say vertical asymptote, that's what I'm going to go for first. Vertical asymptote. Take that denominator, x squared minus 4, and say that can never equal 0, right? You can never divide by 0. What values would make that illegal? Hopefully you can pick them out. X cannot equal 2 or negative 2. Okay? So there's your vertical asymptotes. X cannot equal positive 2, X cannot equal negative 2. Okay? How about horizontal asymptotes? What's that going to be? Okay, no. This is when what a horizontal asymptote is what's happening in the long run as your x gets very large negative or very large positive. Okay? What you look at there is the ratio of the leading terms. So what I would first do is rewrite this ever so slightly as to be 2x squared minus 18 over x squared minus 4. Look at the ratio of your leading terms. What is that? Say again? Ratio of 2x squared over x squared. Not that hard. Is it? It's just 2. And it's y is equal to 2. Horizontal asymptote, y equal to. Because you see the x squareds cancel out. And you're left with 2 over 1, 2. And that's a y. Because alpha of x is equal to that. Y is equal to. There's your horizontal asymptote. Okay? Oh boy, what's next? Next are your extrema, max min. Now, where is that going to be true? Okay, that's where your first derivative is either undefined or 0. Okay, now, before we go any further, and I should have done this at the very beginning, we kind of did it here, okay? Your vertical asymptotes tell you x cannot equal positive 2 or negative 2. So I like to, as soon as I see that, write x cannot equal plus or minus 2. Ever. Ever. So those are not candidates for places where your first derivative is not defined, because the function's not defined there. So don't even count those. Okay? So, what we've got to do then, and again, we're probably better off in this first format, or this other format, alpha of x is equal to 2x squared minus 18 over x squared minus 4. Okay? How are you going to find your critical values? Take a derivative. Very good. And in this case, what rule do you use?
No, it's true. What we talking about?
Okay, when you take a derivative, there's several techniques or rules you use for taking a derivative. What are you going to have to use here?
How is it?
inequality maybe a little bit, but the first and foremost is it's a division, right?
Okay.
What rule do you have to use for that? I was expecting Nolan to speak up. It's his favorite. Huh? Okay. Quotient rule. This is a quotient here, isn't that a ratio? Okay. So what is going to be your first derivative? How does that go? Remember the quotient rule, anybody? It was a long time ago. At least a month. Yeah, quotient rule. How do you do it? Huh? Low, D, high. Low is x squared minus 4. Yep. D high, that would be 4x, right? Minus, not yet, high D low, 2x squared minus 18. And what's D low? 2x over low, which is x squared minus 4 squared. Okay? Now, what are the places you're interested in? Where either that first derivative is
0 or undefined.
0 or undefined. Okay. Yes. Okay. That was our quotient rule. The quotient rule is low, which is the denominator, times the root of the numerator, 4x, minus the numerator times the root of the denominator. There's the numerator, the root of the denominator is 2x over the denominator squared. And the little acronym, acrostic, or whatever, the easy way to remember that is low D high minus high D low over low. If you find that helpful, okay? Frankly, I do it denominator times the root of the numerator minus, yeah. Okay, good. Anyway. Okay. Let's go on and simplify that a little bit. And then I'll go back and ask the same question again. So if you multiply this through, this will be 4x cubed minus 16x minus 2x cubed plus 36x. Did I do it right? Over x squared minus 4 squared. Simplify that, or that would be 2x cubed plus 30x over x squared minus 4 squared. Okay. Now, that is your first derivative. What are you interested in here? I asked this before, yeah. Okay, sorry. Where is it? Well, listen. You're right. No? Here? Oh, you're right. That's the one. Oh, yes, very good. Glad you caught that. Okay. And that makes it even better, doesn't it? Thank you for catching that. Okay. Minus 4x cubed. Because now they go away. Okay. And you're left with 30x. Did I do that part right? I think so. 30x over that. All right, that makes it even easier. Okay, so what are you interested in for that first derivative? Either where it's equal to 0 or undefined. Now we know it's undefined at x equal plus or minus 2, right? But that the whole function is undefined there. So just because the derivative there doesn't make that a critical point. Because you can't. I mean, that would only be if the function is defined there and this isn't defined, then it becomes a critical point. If the whole function is not defined there, don't even go there. Okay, and that's why it's important to locate that. So the only other thing is where it's equal to 0, and where is that derivative equal to 0? 30x there, by the way? Well, the numerator is equal to 0. Where is that numerator equal to 0? 30x. Add x equals 0. Okay? So there is your one and only critical value, because we don't deal with where the function is not defined. If the first derivative was not defined somewhere that the function was, yes, we look at those. But we don't look at places where the first derivative is not defined if the function is not defined there. Okay. So our critical point is x equals 0. The critical value. Well, what is, we've already done that. When x equals 0, it's 9/2. We've already found that value. So that is a potential extreme value. Okay? How could we tell whether that is a max, min, or neither? Okay, I'm going to clean this up ever so slightly. Okay? Take a second derivative. Excellent idea. Excellent idea. Okay? Here's your first derivative. Let's take the second derivative. F double prime of x. And what's that going to be? Say again?
What's the number?
Okay. That's what I was trying to clean up before, but you got ahead of me, okay? That's a 30x and this is a x squared minus 4. That's so ugly. Okay, let me see if I can. Squared. Okay. X squared minus 4 squared. There's your first derivative. So, what do you guess the second derivative would be?
X squared minus 4.
Yeah, you got it. Okay, now in this case, I don't know if this is what you were doing. I like the idea, I know Nolan doesn't, but I like the idea of writing this as 30x times x squared minus 4 to the minus 2. And then do a product rule, okay? I know he likes quotient rule, and it's fine, it works perfectly fine. But if you rewrite it like this and then do a product rule, what would be your first derivative, your second derivative? This is the first derivative. What would be your second derivative? Derivative of that. You tell me. How does the product rule go? Or you can do quotient rule. Either one, I don't care. But just do something. Quotient rule? Okay, do product rule. I don't care.
30x.
30x.
2x.
Okay. Times 2x. I'll buy that.
Doesn't the 4 go away?
Say again?
The x squared minus 4, that 4 goes away, so it's just 2x.
Okay. I got, okay. For product rule, you're doing the first times the derivative of the second.
Yeah.
And the derivative of this part is 2x.
Yeah.
And then what's the rest?
It's done.
Nah.
Oh, you got a chain rule?
Yeah, well, you got to do a power rule. You did the chain rule part. That's good. That's the chain rule part. The power rule, though, is what you didn't do.
I was doing the inside rule. I was just doing
Yeah, the inside is the chain rule part. What's the outside part?
-2.
-2 times x squared minus 4 to the minus 3. Okay? And that's, yeah, plus 30 times x squared minus 4 to the minus 2. Perfect. Okay? Now, I'm going to need some more room to write that out. Okay?
The last part.
What's that?
The last part.
This right down here?
Yeah.
That's a plus. Okay. What we did was product rule. The first times derivative of this. There's the first. Derivative of this, and whichever way you want to do it. I usually start with -2 times this to the -3, then chain rule times 2x. So that's the derivative of that. And then the second part is the derivative of the first times the second, which is just that. Right. Okay? Now, I'm going to take that up top and spell it out a little bit better. Sorry, my cord gets all wound up here. Okay. I'm going to start with the first one here. This is f double prime, and that will be 30 over x squared minus 4 squared. Okay? And then this is going to be a minus, because you see there's the minus sign. Okay? I've got a 2 times 2 is 4 times 30 would be 120. X squared, right? X times x is x squared, all over x squared minus 4 cubed. Okay. I think that's what my second derivative is. A little bit simpler form. See, that's minus 120 x squared over that. All right. Now, why did we take the second derivative anyway? It was so long ago we decided to. Why were we doing that? Well, it says analyze and sketch the graph off. Okay? There's two reasons, at least two, to take the second derivative. Okay? Back up and get a big picture here. Okay? Your first derivative, we set that equal to 0, and we said that first derivative is equal to 0, x equals 0. And that was at this point right here. Okay? Now, the second derivative is going to tell us whether this is a relative minimum or maximum, right? If you put x equals 0 in for here, that was for your first derivative is equal to 0, you should be able to tell whether this is a max or a min. Okay? So put an x equals 0 in here. X equals 0 here makes this, okay, -4. Square that.
16.
Positive 16. So you got 30 over 16, which is 15 over 8, or something like that. Okay? Some number. Okay? 15 over 8, I think it is. Okay? Put a 0 in here, and that's 0. So there's a positive value. So that says that your second derivative is positive, right? At this point. Second derivative is positive, that means it's concave up, meaning this point is a minimum. Okay, so we found out that the only place where you have a critical value, x equals 0, that is a minimum, so we have that. All right. Now, what we haven't done is set this one equal to 0. And now we need to do that, don't we? Because that's going to tell you whether we have a point of inflection anywhere. Now this takes a little bit of doing here. Let's get that over a common denominator. Your common denominator is going to be x squared minus 4 cubed. Okay? Which means the first has to be multiplied by x squared minus 4. So that's 30 times x squared minus 4 minus 120 x squared. Right? And 30 times x squared is 30 x squared minus 120 minus 120 x squared. Okay? That's over x squared minus 4 cubed. Okay? To set that equal to 0, and by the way, let's simplify that a little bit more. That would be minus 120 minus 90x squared. Okay, over x squared minus 4 cubed. Okay? Okay. Is that ever equal to 0? Okay, again, it's not defined at the same 2 points. It always is not defined, plus or minus 2. The function's not defined there. Don't worry about those big points. But what we are interested in is where that numerator is equal to 0, and that would be where that numerator is 0. That would be, I sure hope I've done this right. This is in so deep. Minus 90 x squared minus 120, where that's equal to 0. That would be, let's just make both of those pluses. That would be, and let's divide by 10, okay, at least. And then let's divide by 3. That would be 3x squared plus 4 equals 0. It looks, okay, so that would be 3x squared is equal to, whoa, 3x squared plus 4 is never equal to 0, is it? Because x squared is always positive, 3 is always positive, and that can never be negative. So it looks like there's no place at all where your second derivative is 0, okay? So your second derivative appears to be, if you go back and look at this then, if you write it in this form, your second derivative is always, yeah. I'd say let's, my screen is just too full. I can't see what I'm writing. Let's, I think we got most of it done. Let's end this, and let's see what the book did. And I think we'll be a lot better off, okay? Analyze the grip, domain, all real numbers except x cannot equal plus or minus 2. And that's what I said. Write that on the side as soon as you write down the function. X cannot equal plus or minus 2. Ever. Ever. Okay? So that's your domain. Your range, that's kind of hard to see right off the top, but it's negative infinity up to 2. I don't know how they solve that. Okay? And from 9/2 to positive infinity. Okay? I know how they got the last part. But anyway, x-intercepts, minus 3, 0, and 3, 0. Yeah, we got that, remember? Those were our x-intercepts. Set that numerator equal to 0, okay? Your y-intercept, 0, 9/2. Yes, we had that. Set x equals 0, and you get what y is, okay? Vertical asymptotes, those places where it's not defined, x equal minus 2 and x equal positive 2. I like to say x cannot equal negative 2, cannot equal positive 2. Doesn't matter. Okay, that's your vertical asymptote. Horizontal asymptote, y is equal to 2. We got that. Okay? Symmetry with respect to the y-axis. Why was that? Because this is an even function. All your x's are even, so whatever happening on the left is happening on the right. I didn't say anything about that, but that's the case here. Okay, you have an even function there. So your symmetry is with respect to the y-axis. Okay, first derivative was that. Is that what we got? I think it was, wasn't it? Second derivative was that. I'm pretty sure, yeah, we got that too. Okay, critical number, only critical number, x equals 0. Okay. Points of inflection, absolutely none, because the second derivative is never equal to 0. 20 is not equal to 0, negative 20 is not equal to 0, this thing can't be equal to 0, so there are no points of inflection. We did see that. The critical number, x equals 0, what they haven't done yet was identify that as the VA minimum. The test interval, they go and do test intervals. Why? Okay? You can tell just by your second derivative, I think. Okay? We didn't do test intervals. I was saying that we didn't really have to. But, okay, where did they get their test intervals? Okay? Remember, you have vertical asymptotes at -2 and +2. We have a critical value at 0, 2. We didn't plug this in. If you go back to your original function and plug in a 0, you get a 2.
Wait, did you have? I thought you had 30x.
Say again?
Did you have 30x?
30x?
Yeah, you wrote 30x.
I think I must have made an error there. Okay. Yeah, that's what I was thinking. I didn't remember a 20x. It still gives you the same thing, that your x equals 0 is your critical value. But you're right. I think I did, but I've already erased it, so I can't go back and look at that. 0, 2. I'm trying to remember. Did we have that? I'm sure we did, but. It's 0, 9 halves. So where did they get 0, 2? Oops, going the wrong way. Oh, I know. Okay. Not much. Okay, I understand this one and that outside the vertical asymptote. Oh, I see what they did. And then they just picked the value inside. Okay. Yeah, okay. These are intervals, I'm sorry, that's it. From negative infinity to -2, but not -2 because it can't equal -2, okay? From -2 to 0, from 0 to 2, and from 2 to positive infinity, okay? Those aren't points, they're intervals. That's what I was getting thrown off by. Okay, now they do the first and second derivatives everywhere there, and see, to me, this is a useless line to put here. That's a vertical asymptote. Don't evaluate anything there. The function can't be there, okay? Just list it vertical asymptote. Don't try to do this, okay? X equals -2. That's undefined. X less than -2, out here. First derivative is negative, second derivative is negative, so it's a decreasing function, concave down, it's just going downhill there. And remember, I swear, everything they're doing is right. It just seems like in a bizarre order, okay? It's hard to get all this on one screen. They do it on two screens, so it makes it very difficult. So draw your graph here, okay? With what we know so far, x cannot equal -2 plus 2. When x equals 0, you're at 2.5. So there's 1, 1, 1, 1. So, and we know right now that's the minimum. We had already determined that. That's the minimum value here, and horizontal asymptote was y is equal to 2. So you have, here's what your function looks like. Why mess with it any further, okay? This tells you basically everything you need to know. And this is how they can determine the range there. The domain, all real numbers except the vertical asymptotes, okay, plus or minus 2. The range, anything from minus infinity up to 2 and from 9/2 up. And you see that from this. Now, y-intercept was there. We found out that's the minimum because we did our second derivative test, so you know it has to be going up from there. And really, there's no way and our x-intercepts, minus 3, 0, and positive 3, 0. There's no way for this function to do except like that. So why do all the rest of it is fine. But you can look at it and tell that has to be concave down, concave up. Only one first derivative equals 0. You can get it done way faster than by doing the symmetry is fine, the first derivative is fine, but you know, what's the point of doing all the test intervals? You already had everything you needed to know when you had the first your y-intercept, x-intercepts. That the x-intercepts provided you a value here and there, so there's no reason to test anything else there. Your second derivative test told you that was a minimum there, so there was no reason to do any test intervals there. It just seems like to me they're going crazy trying to use every technique they can when they're just not even necessary. So sorry about this. So, and sure enough, if you put all this down, you see all this is true, but you can see it just looking at the function. Okay? So I think they get a bit carried away. And that's exactly what it looks like. And that's what we drew, sketched just from what we had. I should have just stopped and done that. Okay. I was trying to follow them, but boy, they go a bit overboard. Okay. As soon as you have the x-intercept here, the y-intercept there, the vertical asymptotes here, the horizontal asymptote there, you got the function knocked. It's just, well, and you find out this is the relative minimum. That's the only additional piece of information you need. Because if you've got a point here and a point there, there's nowhere it can go except in that little quadrant here. Nowhere it can go here except that little quadrant. That point defines it. This one could have been going down like this or up like this. So once you found it was a relative minimum, it's got to go up. Okay? That second derivative being positive there, that nailed it for you. Okay? All the rest of the stuff was completely unnecessary in my mind. Okay? Do the minimum. Okay? Get what you need there. All right. Now, we were talking about slant asymptotes. How are we doing? Okay. The graph of a rational function having no common factors and whose denominator is a degree 1 or greater. Okay. Boy. They phrase this really weirdly. The graph of a rational function having no common factors, when you do the factor your numerator and denominator, no common factors. And here's something that's a bit bizarre. And whose denominator is of degree 1 or greater. Okay, yeah, got it. Okay. I was going to say, this makes no sense. I didn't read this one. 1 or greater has a slant asymptote when the degree of the numerator exceeds the degree of the denominator by exactly 1. I would have phrased that first rather than saying this. Okay. The graph of a rational function having no common factors whose denominator, having no common factors, if the degree of the numerator is exactly 1 more than the degree of the denominator, then it has a slant asymptote. Okay? Like this. Here's your rational expression. Degree of the numerator 2, denominator 1, exactly 1 difference there. What you do, long division. Okay? The long division gives you f of x equal x plus. Now, do y'all remember how to do long division of polynomials? Yay or nay? Like a little refresher? Okay, let's do it. Okay. Okay, I'll do it here. There's not much room, but I'll do it here. X minus 2 into x squared minus 2x plus 4. Okay?
That's another way you do it.
What's that?
It's another way you do it too, right?
I can't hear. You do this and do that. Is that what you're saying?
It's another way you can do it, like just 2.
Okay, you're doing synthetic division. And that works on this one perfectly. Okay? Now, here's when you can use synthetic division. If that denominator has a coefficient of 1 and an exponent of 1, that's the only time. If this is an x squared minus 2, you can't do it. 2x minus 2, you can't do it. Okay, well, 2x minus 2, you can factor out 2 and you could do it. But yeah, this one you could do that. So you want to go on and do that one? Okay. But I was going to show, let me show long division, then I'll show you synthetic. Okay. X will go into x squared, x times x is x squared, x times negative 2 is minus 2x. Now we subtract, which is change signs and add. Make that a minus, that a plus, and that goes to 0, that goes to 0. You have a remainder of 4. So it's x plus 4 over x minus 2. Remember when we did division, we would do your remainder over your divisor. So that's what it is. So that's exactly how they got this. Okay? Now, synthetic division. And again, it only works when your coefficient is 1 and your exponent is 1 for that divisor. If that's the case, then change the sign of the last number. Make that a 2 on the outside. And then only write down your coefficients. 1, negative 2, 4. Okay? Skip a line, draw a line, bring down the 1. Then multiply. 2 times 1 is 2. Add 0. 2 times 0 is 0. Add 4. There's your remainder. So it's x, put the coefficient, the variable back in, x plus 4 over x minus 2. So you get the same answer, okay, either way. Now, here is your slant asymptote. The line y is equal to x. That's your identity function, okay? And then this is going to be approaching that on this side and that side. We'll see how that works here. See, there's your slant asymptote, y is equal to x. And then your vertical asymptote, x equal 2, you can't ever touch that. You're not going to touch this one, so you're going to be in between this sector up here and this sector down here. Now, you might say, well, how do you know it wasn't this sector here and that sector there? Pick a point that's on it, not x equal 2. Easy one would be x equals 0, right? Pick a point, x equals 0. And what's your answer? 0, 0, 0. 4 over negative 2. That's negative 2. If this one's here, that one's going to be up there. So just pick some easy point, evaluate. That lets you know whether you're over here and here, or if you're here and here. And when 4, 0, no, I'm sorry. X equals 0, the f of x would be 2. So 0, 2 puts you here, so then this one has to be there. So there's your slant asymptote. And or whatever it's worth. Whoa! Is that all? Okay. That's the only one they do. Okay. We did 1. We just did 2. They don't do 3, 4, and 5. Less.
And 6.
3, 4, 5, and 6. You're right. Okay. You want to do those quickly? Okay. They don't leave us a lot of white space to use, do they? We'll do them here. Okay. Let's do example 3. Analyze and sketch the graph of this function. F of x is equal to x over the square root of x squared plus 2. Okay. What would be your approach to analyze the graph of that function?
We don't want radical in the denominator, so try to get rid of that.
Okay. That isn't a bad idea. Second?
The denominator by itself and
Okay.
numerator.
All right. If I'm hearing you right, you're saying multiply the numerator and denominator by the denominator. Is that right? Yeah. That is a legal move. That will make this the square root of x squared plus 2, square root of x squared plus 2. Okay. No, I mean, that's fine. It's a perfectly legal thing to do. Okay, and this will give you x times the square root of x squared plus 2 over x squared plus 2. Okay. It's a fine thing to do. There's nothing wrong with doing that. Okay? In fact, it may make it easier to see. I don't know. Okay? But the main thing that you've got to do is let's go back and do those points that we did before. And I think it's actually a little bit simpler just to use the basic function. We may come back and do this if it helps us. But let's just go back to the basic function, okay? We know how to... Okay, we know how to do this, and we'll come back and do it if it helps us. But let's just keep it a bit on the simple side for now, okay? And let's see what we got, okay? What are the key things that we look for? Okay, x-intercept. Let's start there. What's going to make the x-intercept? Where y is equal to 0, and what's going to make that y, which is your f of x, equals 0? For this to be 0, that means your numerator has to be 0, right? Okay, so x equals 0. There is your x-intercept, okay? So x-intercept is x equals 0, but then what's the y value? If you put a 0 in for x, what's your denominator? That's going to be 0 too, isn't it? I mean, the denominator is not 0, but your y has got to be 0 too. So yeah, 0, 0, that's your x-intercept. Which, guess what, is also your y-intercept. That's where, when you plug in x equals 0, you get 0 over that. So yes, that is your x and your y-intercept. X-intercept and y-intercept. Both the same, okay? The only intercept you have. Okay? What else might we be interested in?
So y-intercept 0.
Yeah, because when x equals, okay, your x-intercept is where y is equal to 0. Y is equal to 0 only where x is 0. With 0, 0, that's your x-intercept and your y-intercept. Okay? And it's the only one of either one. Okay. Now, okay, horizontal and vertical asymptote. Which you want to do first? Horizontal, okay, horizontal asymptote. Okay, now that's the ratio of your leading terms, okay? And it's basically an x over x, so that looks like where y is equal to 1. The square root of x squared is x, and that'd be x over x is 1. Now, I'm not totally convinced of that, but for right now, let's go with that. How about vertical asymptote? That's where that denominator is 0. Where's that denominator 0? Say again? Never equal to 0. Because no matter what x you put in there, you square it, you get a positive number. Add 2 to it, you get a positive number. Square root of a positive number is a positive number. Never equal to 0. So no vertical asymptote. Okay? All right. Those are basically your easy things. Anything else? I don't think there is anything, right? What's that?
The extreme. The extreme.
Second.
You said the extreme.
Yes, that's the next one. Okay, this is your pre-calculus part. Now we get into the calculus part. And which one you want to do first? The extrema. So we're going to do. Now this is where I would rewrite this. Some people might not, but I would. And I would rewrite this as x times x squared plus 2 to the negative 1/2.
And that's using the power rule?
Yeah, and now I'll use the product rule, which will use the power rule as well. You can use the quotient rule, but even then I would write that as x squared plus 2 to the 1/2 in the denominator. I prefer it, and it's hard to see. Let me get that line out of there. Okay. Now, so that's your f of x. What's f prime of x?
2x times negative 1/2 x squared. Oh, yeah, that's it.
And you still have the multiply it by the x, right?
Yeah, that was just going to be 1. I thought it was 1.
What's that?
What you just did?
I don't know. I was trying to do what you said, but I may have misunderstood. Okay. Now the product rule would be take the first times the root of the second, which is what I thought you were doing.
Yeah, I did.
Well, the first is x times, and then you did the inside part 2x, so that makes 2x squared, right?
I can get 2x squared.
Okay. X on the outside.
Oh, okay.
Okay. And then 2x on the inside. But then we still got to do this part, which is minus 1/2 times this to the minus 3/2.
You got x on the outside, you take the root of the x, that would be 1.
Okay. All right. Product rule is first times the root of the second, right? Okay. So you have an x times the root of this. The root of this, I thought you started with the 2x, the inside part, right? So 2x. Well, you already had x out here, so that would be 2x times x is 2x squared. And then, the derivative of the outside here was negative 1/2 x plus 2 to the minus 3/2. I needed one more parentheses there to close it off.
What if the x was a 3x?
What's that?
What if the x was a 3x?
If this had been a 3x up here, is that what you meant?
Yeah.
Yeah. Then that would have been a 3x here, and then that would have been times the 2x would be 6x squared. Yeah. Okay. So there's the first part of the product rule.
So
What's
you
this?
take the root of the outside.
Right. So that's plus 1 times x squared plus 2 to the minus 1/2. Right? Yay or nay? Okay. It's this times the derivative of that, which x times, and then 2x would be 2x squared, times the negative 1/2, this thing to the minus 3/2. So that's the derivative of the second. Okay? Plus the derivative of the first times the second, which is just that. Right? Yay or nay? Okay. Now, let's clean that up a little bit. Ooh. Okay, one thing I'm going to see is
What about the x? The original x?
the original x.
I mean, like, yeah, like the x on top. So if you're doing the product rule.
Yeah. It's this times the derivative of that,
Yeah,
right?
I know.
And derivative of this, he started with the chain rule part,
Yeah,
2x.
Isn't that 2x minus 1 times 1/2? Isn't that all the chain rule right there?
Right, but I had the x out here, so the 2x from in here times the x gave you 2x.
Oh, I didn't see your squared up.
Oh, I see. Okay.
It probably did.
And then I noticed that the 2's can cancel out. One's in the denominator, one's in the numerator. Okay? So now I'm going to rewrite that ever so, well, majorly, I guess. I'm going to start with the positive part. That's 1 over x squared plus 2 to the 1/2. And then it'll be a minus, because of that minus sign there, x squared over x squared plus 2 to the 3/2, because that was a minus 3/2 there. Okay? Well, I noticed that the difference in those denominators is x squared plus 2, so this will be x squared plus 2 over x squared plus 2 to the 3/2. I just multiplied by that, minus x squared over x squared plus 2 to the 3/2. So now we got a common denominator, and you got x squared minus x squared. That's going to be 0. That's be 2 over x squared plus 2 to the 3/2. There is your first derivative. I can't write. Okay. Now, is that ever equal to 0? No, because 2 is not 0. Okay, wait, did you go back? No, I can't.
I don't even know if I did.
Okay, wait, okay. All right. What I did you agree with this line here? Were you all right with it?
Yeah, I got that for it.
You did? Okay. Canceling out the 2's for that. Okay, well, what I did, I put this term first. It's 1 over this thing to the 1/2, right?
Yeah, I did that.
And then the minus here, that's why I started with plus. I don't like starting with minus. And this was x squared in the numerator, and this thing in the denominator, that's to the 3/2, right? Okay. Now these two denominators differ by x squared plus 2, right? X squared plus 2 times this will give you that, right? Okay. This is x squared plus 2 to the 1/2. This is x squared plus 2 to the 3/2. If I multiply this by x squared plus 2, which is x squared plus 2 to the 2/2, then that would become 3/2 too, right? Okay. All right. If this were 1 over a to the 1/2 minus a squared over a to the 3/2, right? Is that all right? Okay. That's sort of like what we've got here. We've got this thing to this, something over here, and this is to the 3/2. Same base. Okay, yeah. So to get the common denominator, I have to multiply this one by 2/2, right? And that'd be a whole. So it'd be a up here, which is exactly what this thing up there. Okay, got it? Okay. Now, and then you're okay with the rest of it. All right. All right, so the point being, here's your first derivative. That's never equal to 0. The only way it would be 0 if 2 are equal to 0. 2 is not ever equal to 0, right? So this first derivative, there's no place where it's ever equal to 0. Well, is there any place where it's not defined? Okay? And that's not true either, because this thing down here can never be equal to 0, right? So we already went through that. So there's not point of inflection, no extremum. No first derivative equals to no extremum, no max, no min. Okay? Now, I guess we ought to do a second derivative since we're here. So f double prime of x. Now here I'm going to rewrite this again to be 2 times x squared plus 2 to the minus 3 halves. Now I'm going to take a derivative of that one. Is that okay? Yay or nay? I just rewrote that in what you ever call it form, power form. Yeah, okay. Now, negative 3 halves times 2 would be a negative 3 times x squared plus 2 to the negative 5 halves.
You say negative 3, that's a negative 2.
Second?
You say negative 3, that's a negative 2.
Yeah. Negative 3 halves times 2 would be a negative 3. Oh, yeah. I said negative 3 and wrote negative 2. I'm sorry. The old gray cells ain't what they used to be. Okay. All right. Sorry about that. That's probably where the 30 came from before. I don't know. Okay. And we still have the chain rule part, which would be a 2x, right? All right. So this becomes minus 6x over x squared plus 2 to the 5 halves power. Okay? Now, that one is equal to 0 somewhere. Where?
0.
At x equals 0. Okay? Well, x equals 0, we're at 0, 0. So the question is that a point of inflection or not? Okay? And I think what we have to do is look to the left where x is equal to a minus 1, and that then makes this positive, and this thing is going to be positive. Okay? Look to the right where x is 1, this becomes negative, so sure enough it is a point of inflection there because it changes the sign of the thing. So it's concave up to the left of 0 and concave down to the right of 0. So we do have a point of inflection. Okay. Now, what did it say? Do this. Sketch the graph of a radical function. Yuck.
Before we move on, can we...
What's that?
I said before we move on, kind of finish writing this almost done.
Okay. Yes.
Can you do a product rule for me real quick? I ain't trying to knock you off the list.
Okay. I heard something about a product rule.
Yeah, can you, I was going to ask you, can you do one for me real quick?
Sure.
Like square root of x times 6.
Okay, say that again.
Square root of x times 6
Square root of x
times 6 minus r to the 6.
times 6 is what you said? Okay, I'll put the 6 in front.
It's in parentheses.
Oh, I'm sorry.
Minus r to the 6.
6, okay. Wait just a second, let me. Okay. 6 what?
Minus x to the 6.
Minus what?
X to the 6.
X to the 6. That's what you're wanting to do.
Yeah.
Okay.
How do you use the product rule?
Okay. Okay, first thing I would do, I'd rewrite this as x to the 1/2 times 6 minus x to the 6. Right? Okay. Now here's the product rule.
I change the 1/2.
Because this is square root of x. Right? Okay. Okay. Now, where do you want to start? You want to start with x to the 1/2? You can either do first times the root of the second or the second times the root of the first. I don't care. You tell me.
I do the second time.
Second times the root of the first? Okay. Okay, second would then be, okay, if this is your function, f of x, then your f prime of x, okay, you said the second, which is 6 minus x to the 6, times the derivative of the first, which would be 1/2 x to the minus 1/2. Okay? Plus the first x to the 1/2 times the root of the second minus 6x to the 5th. That'd be it. Yeah, I mean, I'd clean it up a little bit, but that's it. That's the product.
How would you clean it up? I got that part.
Okay. This doesn't clean up nicely, but
That's
it
what
does.
I'm saying. I got that part.
Okay. So if I were going to clean this up a little bit, and there's not really a lot you can do to this, but there is something. I would write this as, I'm going to write it up above because I don't want to mess it up with our problem that we got now. Okay? So let me write it up above. Okay. Here's your f prime of x is equal to. Okay. I just like leading off with the positive part, and this first part is the positive part. And what you have in the numerator is 6 minus x to the 6th, okay, over 2 times the square root of x. 2 times, that's x to the minus 1/2, right? Put it back in radical notation. Then I'll do a minus here, and this would be 6, and x to the 5th times x to the 1/2 would be, you add exponents, that would be x to the, that's 10 halves plus 1/2, 11 halves. I mean, it's just another way to write it, but.
I just didn't know if I had it all up.
Yeah, and you could leave it all out. That's perfectly fine too.
Oh, I have to find it.
You don't have to, no. I was just trying to,
Oh, okay.
yeah. But you see, when you combine this, you simplify it. So that one isn't going to simplify no matter what you do, so you can leave it any way you want.
That's why I was wondering.
Yeah.
Simplify.
This one will. Okay. Now, let's get back to where we were.
Okay.
No, that's perfectly fine.
He was just finishing this problem. I got it written down. So we can-
Okay, so what I'm going to do here is I'm just going to write down my first derivative, f prime of x, and this is where we ended it. I'm going to leave it in this form, 2 over x squared plus 2 to the 3/2 power, and then f double prime of x is equal to minus 6x over x squared plus 2 to the 5/2 power. Okay, just to have those done. Okay, now I'm going to erase most of the rest of this. Sorry, I hope I'm going to erase something we'll need later. I hope I've done it right. And if I haven't, I'll just say, you figure it out on your own. No, I don't know what I would say. You find my error and correct it and come up with the right answer. Okay, that's a good professorial thing to say, right? The rest is left to the student, you know, when you get too deep and you can't figure out what else to do with it. Okay? All right. So what does this tell you? It says sketch the graph of this rational function. Okay. The only intercept we have is at 0, 0. Horizontal asymptote, y is equal to 1. Vertical asymptotes, there aren't any. Okay? Oh, here's the thing we didn't do, and probably we should have. I thought of it earlier, but then someone asked a question, I forgot to go back to it. Okay? Here's something to notice. That denominator is always positive, right? This is your original function. Okay. So, the numerator is going to be positive on the right, negative on the left, and it's got to pass through here. Okay? So, that says this thing, whatever it's doing here, it's going to be approaching that vertical asymptote. Okay? Now, what is happening when x is negative? That denominator is always positive, so this stays negative, but it looks like to me it approaches down here. I have nothing but a gut feeling for why that's true. Oh, I know. Yeah. This ratio here is 1 in that direction, but it should be a negative 1 in this direction. Because you see, this would be a negative, and that would be a positive. So yeah, that's exactly what's happening. Let me go back and correct this. And this is a bizarre thing for them to do to you, but they did it, okay? The horizontal asymptote is y is equal to 1 for x greater than 0, and y is equal to negative 1 for x less than 0. Okay, so basically your function is doing something like this. Okay, and that's what makes that your point of inflection. Okay, because it's second derivative is concave up to the left, concave down to the right. That's what you got. Okay. And, okay. And if you look at your graph in the text, that's exactly what theirs looks like too. Okay. That was a rather bizarre one in my mind, but that's exactly what you get there. Can I go on to example 4? How are we doing on time? Yeah. Do you have any questions on this before we leave it? Okay. What's that?
I was trying to say it's just a lot, but I understand it's more.
Okay. It's that was a bizarre problem. It truly was in my mind. Square roots in the denominator, that's rather strange. Okay. Let's do example 4. Analyze and sketch the graph of this one. F of x is equal to 2x to the 5/3 minus 5x to the 4/3. Is that right? I believe so. Okay. All right. Another rather bizarre one, because now we're doing with cube roots. And what I failed to do on the last one, let's not fail to do on this one. Okay? Now, what's your domain of this function? We didn't do that before, or I should have done. What's the domain of that function?
Sure, because
Second?
I'm trying to think of it because I'm not sure. It's all in nominal, but
All real numbers.
All
And
real
the
numbers.
reason is because these are cube roots. You can take the cube root of a positive number and a negative number. Doesn't matter. If that was a square root, you'd be stuck to only taking square roots of positive numbers. These are cube roots, because that 3 is in the denominator.
okay.
So all real numbers. Okay?
The fact that it's a fraction saved me that throwing me off because I'm like it's
Right. Okay. So your range of this, ranges are always hard to do until you figure out what the graph looks like. And then you can figure out what the range is. Okay? So this is going to be a little tough to figure out the range so far, but at least we know it's going to be all real numbers for the domain. Okay? Now, what might be the next thing you want to do? You got the domain as all real numbers.
We going back to what we just did?
Yeah.
Gotta find intercept.
The intercepts?
Yeah.
Okay, which one you want to go for first? Y-intercept? That'll be the easy one. You're going for the easy one, right? Y-intercept is for what's always what? X is 0, okay? So you put an X equals 0 in there, and what do you get? 0, right? Okay. So that's not only your y-intercept, it's also your x-intercept. But could you have more x-intercepts? Let's think about this a minute. Because if y was equal to 0, that could also be implying that 2x to the 5/3 is equal to 5x to the 4/3, right? If this is equal to 0, then you could add this to both sides and you get this, right? Okay. So cube both sides of that, and what do you get? See, the cubing is going to get rid of your denominators here, right?
So you say you want to have 5 and 1.
Second?
5 and
No, that's the 4/3. 5x to the 4/3. He's making fun of my writing, I can tell. Okay, I'm not hurt. I can handle it. You know, it doesn't hurt too badly. So let's cube both sides, and you get 8x to the 5th is equal to 125 x to the 4th. I'm not liking this at all. Okay. Yuck. And then let's divide both sides by x to the 4th. And you have x is equal to 125 over 8. There's your other x-intercept. Okay? Second?
Oh, you got 1 x left. After you divide this.
Yeah, I divided both sides by x to the 4th. Okay? You all right with that? This is a really bizarre problem. So anyway, x is 125 over 8, which I think is something around I don't know, about 13 and something another. Yeah, 13 and some odd things.
15.62.
Second?
15.62.
15.62. Okay, I was saying 13. 15.62. Okay, so it's some other number. So you do have another x-intercept. Okay? So those will be x-intercept is that plus 125 eighths 0. Okay? Okay. So you got 2 x-intercepts and 1 y-intercept. And the y-intercept is an x-intercept. Okay, so that's done. Next. Next. Asymptotes. Which one you want to go for?
Horizontal.
Horizontal. Okay, a horizontal asymptote is what's going to happen as this is going extremely large, positive or negative. Okay? And as x is very large, positive or negative, these are going to infinity, I'm pretty sure. So I don't think it has any horizontal asymptote. Because you see, when x gets very large, positive, this is going to dominate, right? Because that's to the 5th power, that's to the 4th. But as it gets very large, negative, a cube root is negative, so this again will dominate, and that will be a very large negative number. So I don't think there's any horizontal asymptotes. None. Now, how about vertical asymptotes? There's no place where your denominator is ever, you don't have any denominators, right? So there's no vertical asymptote, I don't think.
You're saying there's no denominator. What do you mean there's no denominator in the original function?
In the original problem, there's no denominator there. So there's no place you have a vertical asymptote. Okay? So what we're left with is analyzing your derivatives. So what's your f prime of x? You tell me. Okay, we're running out of time. Are we going to make it? You think we can?
Yes. How do you do it? You bring it down
Product rule. Power rule. 10/3 x to the 2/3 minus 20/3 x to the 1/3, right?
Yes.
Okay. And if you set that equal to 0, the only place that's going to happen, I think, is at x equal 0. Okay. There's no place where it's not defined because cube roots are defined everywhere. So that would only be at x equal 0. Okay. So there you have a potential first derivative, an extreme value. Let's do your f double prime of x. And what would that give you? Help me. 20/9.
Oh, yeah.
20/9 x to the minus 1/3, right? That's a 1. Yuck. That's a 1/3. Minus 20/9 x to the minus 2/3, right? Okay. Well, let's factor out a 20/9. I'll be all in favor of that. X to the, I don't need that parentheses there. See, how do I want to factor? Let's factor out a minus 2/3. And that leaves us a x to the 1/3 minus 1. Right? Okay. You set that equal to 0, and that's either going to be at x equals 0 or at x equal 1. Okay? So you have two places where your second derivative is 0, and one of those is where your first derivative is 0. So I have a feeling that's going to be an inflection point, and that, no, we're not sure about that. I think that will be an inflection point. I believe that in will too. So I don't know. Let's see.
I thought it had to be a difference. Like one had to be positive, one had to be negative. The 0 is neutral.
Yeah. It's a bizarre looking function, to say the least. And time's up. So why don't you play with that at home and wrap it up. I think you'll see that everything does sort of pan out. We'll begin next time with example 5. Now that means we've got just 2 examples left to do. I think you can do any of the either 5 or 7. They're both at calcchat.com, and then do any of the odds 9 through 35. They're all at CalcChat. 33 is at CalcView. And then any of the odds 37 to 43, they're all at CalcChat. 37 is at CalcView. And try to do 45 to 49 odds there. Those at CalcChat.com. Okay. We'll pick up the rest of those. Yes, sir.
Yeah, I'm trying to most of them.
Okay. Let me Go on. You want to record this or not? Okay.
I just
Okay.
need to make sure I'm doing it
Yeah.
right.
Yeah.
This part, I'm not sure what to do right.
Okay. This one?
Mm-hmm.
Okay. Okay, I assume that you did 7 times this thing, right?
Yeah, I did the inside first.
Right. Oh, you did the outside. Okay, inside first. Okay, 35 t to the 4th. That's
Then
correct.
I did sometimes that. I got sometimes movement. I can see.
Yeah.
That'd be it.
Yeah, but you can clean it up a little by the 7 times 35, you know, and then I wouldn't do anything else, but yeah, 7 times 35, and then you have,
So you can multiply this one. Yeah, 42 t to 4 times that.
okay. Do the numerical part, 75 times, 35 times 7. You can do that, right?
Oh,
Okay, and that'll leave t to the 4th times this. Don't multiply that. Just leave that as t to the 4th times this thing here. But you can multiply the numerical part.
So I can multiply.
But I mean, there's nothing wrong with that answer. That answer's fine.
So I
Okay.
can multiply 3 and 4 to the 7. That's what you're saying.
Okay.
These whole numbers. These numbers right here.
Yeah, you could do that as well. That would be 12 7. So,
Alright, so do this.
okay. Implicit differentiation. Okay. Remember how you did those? Remember y is a function of x. X is not a function of x, so you just take that derivative, right?
Okay, yeah, I
Right.
get that part.
Okay. And this one you just do that derivative.
I know what you said.
Okay, but this one you do a product rule. That one times that. Okay? But remember, derivative of this is dy dx. Derivative of that is just 3. You know, you got the product to deal with, and then this one you have a power rule.
By that, I'm saying the product was on 3x. You do product rule just for this?
No, of this term and that term. Well, this term doesn't need a product rule. That one does. This one you just do a power rule.
How would you do it?
Well, okay.
I know how to do the product rule.
Okay. This is in. Yes.
Oh,
Oh, okay.
You might want to stop the recording.
I'm sorry.
I see you might want to stop the recording.
Well, I asked him if he wanted this recorded. He said he didn't care. So I figure if I'm telling him the answer, everybody else will be able to hear it.
Yes, okay.
Okay. I need it back because not everybody's turned it in. Okay? Okay. All right. Now, differentiation. Implicit differentiation. So, for instance, this one. Fairly similar problem. 3y squared, but then because y is a derivative, then you do dy dx, right?
Okay, so you have to write dy dx.
Right, okay. Then this one is, derivative of that is 2y, but also times dy dx,
Okay.
okay? And
So
this one is just a minus 5 times dy dx. And this one, there's no y in there, so it's just a minus 2x.
So the x stays. So you just take the derivative of the x and the y's, you have to change them to dy dx.
Well, yeah, you take the derivative of it, and this will be a product rule, and then a dy dx, and this will be a power rule with a dy dx, okay? So you see you get some terms with just x's in them, like these two will just have x's in them, and some terms that have dy dx's in them.
See, that's what confuses me because I don't see an x and a y next to one another.
What's that?
You got two variables.
Okay,
That's what confuses me.
well, that's just a product rule. Let's see if we have one with a product rule. This one sort of does. Yeah, this one does. Okay. See, here's a product rule. So you do the derivative of that, it's just 4x cubed.
Okay.
Derivative of this is a product rule. The first, x
Oh, you're
squared
just
has
taking
derivative of the
of
second.
the y.
Huh?
Okay.
And then the second is the derivative of x times y squared. So you see,
So is it 3x? You did over dy dx. So you just did it for the y.
second
You just do dy over dx for the y.
for the y, yeah.
Oh, okay, so I just think I do power rule all e.
No, it doesn't cancel out. It's dy dx, or I like to do y prime. It's just so much easier to write.
I only get it, like, cause I ain't got no, like over there you got the 2.
Yeah, yeah. Here we had a 2 in front too because
So
it's
it's
2y
a
dy
dy
dx. Right. You just have a dy dx. But then that last one you have
Oh, I did. So I have to do the derivative of x2, right?
yeah. Okay, yeah. The product rule says you do the first times derivative of the second. Derivative of y is just dy dx. It's not y times dy dx.
Oh,
Right.
okay. So 3x times dy dx.
3x times dy dx. Okay. Now you do the first derivative of the first, which is just 3 times y. You see? Okay. All right.
The 2 variables will mess me up. Bad.
It's 3x times y. All right? Derivative of this, which one did you do first? You did this times derivative of this. It'd be 3x times derivative of that is y prime.
It'll be 3
Plus 3 times y. Derivative of this times that.
Oh, 3 1.
Yeah. You see?
Yeah, I get
You
what
see
you're
why
saying.
it is?
Yeah, because that exponent 1.
Yeah.
I do power rule for my side.
Not product rule, power rule.
Okay.
Times y prime. Anytime you have y, you have to follow it with the y prime.
What's my
Chain rule. Derivative of y with respect to x.
What you mean?
Okay.
So I had to multiply times negative 1 to the 5th.
No, 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 no. Okay. What if that y was x squared? X squared to the 5th. Okay? Now, you could just make that x to the 10th, but let's do it this way. That would be 5x squared to the 4th times 2x, right? Chain. Okay, same thing here. Y is a function of x, so you have to do a chain rule for that. You did the outside part, but then you have to do the inside. That's your dy dx.
I'll try.
Okay. Go back and refer to that example 8 at the bottom of page 148. I think you'll find it helpful. Okay.
So about the test.
Okay. All right. Do you want to record this or not?
I mean, he's regarding the quiz, so.
Oh yeah, that one's still out. So.